Magnetic Field and a Loop of Wire by Alexis Anderson, Brianna Rice, and Ashley Coggle.
The main area of interest we investigated was the mechanisms that cause the magnets and electric current to generate the motion of the wire. How does increasing the number of batteries affect the speed of the motor? In order to investigate this, we took measurements of velocity and current for each increase of voltage. We found that with voltage increasing, current consistently increased, the velocity decreased overall. Magnets at the base of the setup created a magnetic field in the upwards direction. The voltage of the batteries generated a current through the circuit, which flowed through the wire loop of the motor. Based on the planes that these two components existed in and what we know of the cross-product rule, we can determine that the force of the system was both coming toward us and moving away from us as the motor spun.
In order to figure out how increasing the number of batteries impacted the speed of our motor, we ran an experiment. We first chose a wire that had 4 loops. We then balanced our loop of wire on the rods of the wooden block. We placed clay down in order to stabilize our magnets directly beneath the loop, making sure our magnets didn't hit the loop of wire. Using alligator clips, we clipped 2 1.5-volt batteries to either rod, as shown in the photo to the right. We did have to spin our loop of wire in order to get our motor going, and once we had a complete working motor, we took a 15-second video of the loop spinning in order to find the velocity using Tracker. On Tracker, we used a single point on the wire to record position over time. We recorded the current using a multimeter. We then repeated this exact experiment using 3 and 4 batteries. Here's the data from our 3 experiments. As you can see, as we increased the number of batteries, therefore increasing the voltage, our current increased. This makes sense considering our resistance never changed, since voltage is proportional to current. We expected to see an increase in velocity as we increased the voltage. However, we found the opposite. Our average velocity decreased as voltage increased, and we believe this is due to software error.
A force is generated from the charges moving through the wire and the magnetic field acting upon them. Because force is the cross product of current times the length of the wire and magnetic field, it travels perpendicular to both in our experiment. Force is pointing away from the loop on both sides, which causes the loop to spin. This picture is similar to our experiment, except our positive and negative sides of the battery were flipped, so our loop spun into the screen or backwards. Limitations and conclusions. The loop travels the fastest with 2 batteries or the smallest amount of current traveling through it. The electromagnetic force equation tells us that as current increases, force should as well. This indicates our results are the opposite of what is expected. Qualitatively, we observe the loop spinning the fastest with 4 batteries, so we know there were some errors in our data analysis. We adjusted the rods that our loop rested on before beginning, and we believe they could have been uneven. This could have prevented the loop from spinning properly and affected our velocity values. Also, we only recorded the spinning loop from the front of the motor. Recording the side of the motor as well could have more clearly shown the rotations of the loop, and we could have counted that over time. Once we put the videos into Tracker, we believe because we only saw it from the frontal view, we could have missed a rotation if the loop spun more than once in between frames, especially with increasing voltage. If we were to repeat this experiment, we would record our loop spinning from a side view in slow motion and ensure that our setup was sound.